Welcome to the fourth installment of the statistics portion of my Math 3350 online course. And today we're going to be talking about proportion tests. We have two basic options. So we can use the Z proportion test, which uses the normal curve, uses a bell curve to provide estimates for the binomial data from a binomial distribution. You either have a success or a failure. So just like coin flips. Situations like the lady tasting tea, those are proportion tests. Now, when we have one or two proportions where we're just counting successes and failures, we can use the Z-test. If we have category variables, or if we have category variables with more than two levels, then we are forced to use the chi-squared test of independence. Now, traditional statistics does use the one proportion z-test and the two proportion z-tests. And we have to use chi-squared. Everyone uses chi-squared. Modern and traditional all use chi-squared for category variables with three or more. Now it's interesting, R actually uses the chi-squared statistic for all proportion testing. And the reason is that it turns out the chi-squared test is more robust than Z. So robust means that you can violate the assumptions but still hold accuracy with the p-values that your statistical procedure is spitting out. So R has just gone completely to chi-squared, which is fine. But if you're going to teach this in an AP Stats class or the current environment, you still have to know how to use Z-proportion testing on the graphing calculator, for example. So we're going to go over both. So if we're going to do both, we have to know our verification procedures. So the big idea with Z-proportion tests is the number 10. We need to have 10 successes and 10 failures, right? This is why we couldn't use it on the lady tasting tea example, because we only had 8. As a matter of fact, it wasn't even quite good enough for chi-squared. Chi-squared was throwing up an error message, if you recall, because we only had 4 successes and 4 failures. So sample size matters. That's what these verification procedures are about. So generally speaking, we're just going to require 10 failures and 10 successes in all our samples for Z-proportion tests. However, with the one prop Z-test, we have to calculate estimated successes. So we take the sample size n times p sub 0. So p sub 0 is the population proportion. We have to either be able to figure it out, or it has to be given to us in the setup of the problem. And you'll see an example of that in just a minute. Now with chi-squared, we require that we have no more than 20% low expected cell counts, and a low cell count is something that's strictly less than 5. Okay, so let's tackle the first situation here. So computers can play chess better than humans now. So even our current world champion Magnus Carlsen doesn't play perfect if you call the best computer moves perfect. So we know that Magnus, even playing his best, is going to match the computer move less than 80% of the time. So if Magnus's accuracy is less than 80%, then anybody else is going to be less than 80% if we do the following. There are a couple little details. So the opening moves, grandmasters sometimes know as many as 20 or 25 of the opening moves, but even amateur players a lot of times know 5, 10, or 12 opening moves. So we strip out the known opening moves, and then there are also forced move sequences where your king's in check and you have to move, like everybody's going to play the same move because it's forced. So that's what we do, or that's what they do to detect chess cheats. They strip the forced moves and the opening moves out, and then they are very charitable, and they give the amateurs a world champion, grandmaster, super GM level of accuracy. Okay, so we are at chess.com, and we're trying to determine if this suspected chess cheat Sam is cheating or not, right? So we find 6 games that he's played recently, and we find 78 moves that aren't forced, that aren't opening moves. And he plays 72 out of 78. He plays these engine moves from, these chess computer engines. So we want to set up a null hypothesis about whether this is possible. So our null hypothesis is, hey, just assuming that he had a great day and he played as well as the best human on the planet can. He played at Magnus Carlsen 80% accuracy level. What's the probability that we would observe this data given that he was guessing these moves with coin flip accuracy of 80%, right? It's randomized accuracy of 80%. Now, chess.com requires, they state on their website, they require a 99.99% certainty of the cheating before they're going to kick somebody off their platform. So that translates into alpha being 0.0001. All right, this is one proportion. Why? Well, we have one sample of 78 moves, we have 72 successes, and we have 6 failures, okay? Now you're going to say, well, we have 6 failures. Hasn't it failed verification? Well, let's set up the null hypothesis, right? The null hypothesis we said was, hey, suppose that the proportion that Sam is playing at, his accuracy level is 80%. Suppose that's true. And by the way, I'll just mention something about this variable right now. What we'd like to do is we'd like to use P. The problem is that at the end of every hypothesis test, we get a p-value, which is the probability that the null is true. So we don't want to use p. Interestingly, there are some stats textbooks that use the Greek letter pi for this proportion, right? We want to have something to represent that. Not a fan personally of either one, especially not the p, but that's why I'm using prop. Why? Well, when we get to our graphing calculator, you'll see that the graphing calculator will use this prop. They just spell out the word out. So I'm going to use the same thing. Then when we use the graphing calculator, it'll make sense. But again, this is the only place we'll use it. When we have 2 proportions, we have a way of subscripting that will help us avoid confusion. So this is just the proportion of Sam's accuracy. And then we're questioning what's the probability given this data that he can get more than 80% right. That's our alternative hypothesis, that no, he's not just getting 80% right, he's getting more than 80% right. Okay, so now is where we do the verification with the estimated successes. So if you recall, right, I had this little note in here about the 1 proportion z-test where we use estimated successes. So n is the sample size, is going to be 78, and then p sub 0 is going to be 0.8 for our example. So let's jump back here, and you'll see what I'm talking about. All right, the sample size is 78. P sub 0, that's the population proportion, right? We're assuming that these amateur chess players, giving them all the benefit of the doubt, they couldn't be any higher than 0.8. So we're using 80% as our P sub 0, our population proportion that we're comparing against, right? Our P sub 0 value goes in the hypothesis because that's what we're comparing against. We have one sample, one proportion, one sample of data, and we have this population proportion we're comparing against. So our estimated number of successes, if we're right about the 0.8, our estimated successes is going to be 80% of 78. In other words, we would expect Sam, actually we'd expect Magnus, right? We'd expect the world champion to get about 62, 63 correct moves out of 78. Sam did a little better than that, so we're a little suspicious. Also, we can calculate the estimated failures. We take 1 minus his successes, right? 1 minus his successes, or if the probability of rain is 80%, the probability of it not raining is 20%, multiplied by the sample size. And so we're estimating that Sam would get 15 or 16 wrong moves, incorrect moves. So we're expecting 62 to 63 accurate moves and 15 or 16 inaccurate moves if he's playing at the Magnus level. So let's run this test. Where are these values coming from? Well, one final thing I need to point out is that the statistics here are, the statistic here that we're calculating is p hat. This is the fraction of successes over failure, over total, right? So this is where the fraction 72 over 78 comes in. Okay, so let's grab our graphing calculator, and we can go to the Stat button, Test menu, and we're using the 1 proportion z-test. This is option 5. And notice it just asks for p sub 0, right? Which for us is 0.8. And it asks for the x, which is the number of successes, and it asks for the number of total observations, which was 78. We had a greater than hypothesis that we're looking at, right? We had greater than here. So we're matching that in our alternative hypothesis row. And then we're going to draw this. Okay, so this is going to be the bell curve estimation, and you're going to see several things, right? You're going to see the p-value of 0.0033, the z-score. So this group of moves was 2.71, 2.72 standard deviations above Magnus's best day, right? That's a long way. We just talked about standard deviation in the last video, right? This group of moves is 2.71 standard deviations above Magnus Carlsen's best day. Does that sound like Sam, an amateur player, could actually do that without cheating? So that's where we're getting Z and P. We're going to run those. So now we have a p-value. So we compare p to alpha, right? And notice that we were using such a strict requirement to kick this person off. We don't actually have enough evidence. And here we would actually fail to reject the null. And this is wrong. I'm sorry. I'll fix that before I put the notes out. So since our p is actually less than 0.05, but it's greater than our actual alpha. Sorry about that. Typo on the slide. But the research conclusion would be that the cheat detectors at chess.com would not boot Sam. Now, I'm pretty sure they'd watch him, and just a few more samples, right? You can actually play around with this in your calculator. It doesn't take very many. It takes less than 100 if he has this same percentage of successes. With less than 100 moves, he'll get kicked off at this level. It's just not very likely. But I wanted to, talk about this level of significance. Sometimes it's better to go away from the default, and they just want additional certainty before they kick people off their platform because people are paying many times to be there. So the biggest cheating scandal ever for standardized educational testing occurred in, drumroll please, the Atlanta Public Schools. And so the next example about cheat detection is related to this article, and you can find out about what happened. We're going to be looking at this scenario right now. We have another scenario in the next video that we'll be discussing about Atlanta Public Schools cheating. And all of the information about the cheating is available at this link. which is where I read about the different things that they did and to create these examples. So check out that link if you're interested. But basically what we're looking at today is this situation. So often children leave items blank, but and you don't want to erase their wrong answers. What's really nice is if they leave stuff blank, you can just fill it in. You can just fill it in. So the cheat busters won't be able to detect any of the eraser marks. However, they can still spot some cheating real fast. How? Well, when kids are working a test, most of them go from start to finish. So the last few questions are much more likely to be left blank. That's the ones they don't get to. And if they don't guess, right, there might be 5 or 6 answers at the end that are left blank. Well, then the cheating staff at APS could go in and just put the right answers for those last few that were left blank. So here's what CheatBuster is going to do. They compare the accuracy rate on the last 5 questions for 30 suspicious exams with the accuracy rate for 25 students from a group, and they have video evidence for this control group that no cheating occurred. So now they have 150 items in the suspected cheating group, 114 of which were correct. And in the control group, only 48 of 125 items were correct. And so we're going to test, again, at a very stringent level, whether or not cheating occurred. Okay, so notice that we have a 2 proportion test, right? We have 2 samples of data. We have the suspicious group, right? 114 out of 150, so that's 1 fraction, right? So this is the test group, right? We have test and control group, right? And so then the p-hat for the suspicious test group is 114 over 150. So the alternative hypothesis is that the proportion of correct answers in the test group was higher than that in the control group, right? So notice the control group is only like, what is that, 2/5? So about 40%, but look at this. This is looking like it's over 60%, almost 2/3. So the percentages look a lot different, and that's what our hypothesis test is going to get at. Our null hypothesis that we're testing is that the proportions in the 2 groups are identical. What's the probability of getting this different pattern of results in our observed data if, in fact, the data were drawn from identical populations? Well, verification is now easy because we're just checking for more than 10 successes and more than 10 failures in both groups. And we had 114 successes and 48 successes. And when we do the subtraction, you can see that all of this is just fine. When you put this in the graphing calculator, and I'm not going to do it, I'm going to show you when we go to the graphing calculator. This is option 6. And we have x1 and n1 we put in, and x2 and n2 we put in, and then we set up our alternative hypothesis. And you can do that on your own time, but when we do it, we get a group of answers, right, that are 6.2 standard deviations away from each other, right? And the probability of this null hypothesis being true, that, hey, they're equal proportions, right? They're drawn from distributions with equal proportions. The probability that that's true, that's 2 times 10 to the negative 10th. 2 times 2 to the negative 10th. So yeah, we're going to reject. I got this alpha level wrong again. Copy paste error again. I'll fix that in the notes. But it's far less than our very conservative 0.0001 level of significance for alpha. So we reject the null, and we have really overwhelming evidence. That's the nice thing about p-values, is that they provide us with real good estimates of how strong the evidence is, right? Well, 2 times 10 to the negative 10th. That's virtually zero. There's almost no chance that this control group had the same distribution that the testing group did. So we have overwhelming evidence of cheating, and that's what eventually got these teachers and staff from the Atlanta Public Schools. Actually, people went to jail, um, and that's how this was the evidence that was marshaled against them. We've seen a one proportion test, a two proportion test, and those are both run, in the classroom. If we have a graphing calculator, then we're going to run those as the proportion tests. Like we said, chi-squared is what R will use for all the proportion testing. But this is one where we will definitely be using chi-squared even for the graphing calculator. So here's the problem. This is why we can't use z proportion testing. We have a category variable here with ethnicity is this category variable, and it has 4 levels. There's only 2 levels, of employment. So the reason this is sometimes called a chi-squared two-way test is because this is called a two-way table, where you have the levels of one variable across the columns, the variables of the other levels, the levels of the other variable across the rows, and then this is a cell count, the number of Asians who were self-employed, or the number of Native Americans who work for wages, the number of whites who were self-employed. So these are just cell counts. So we have proportion data, and we're going to use chi-squared test of independence. And what's the null hypothesis here? So let's think about this. So the question is whether or not there's the same percentage of each of these ethnicities and races is the same percentage self-employed, and does the same percent work for wages. It appears that about 10% of the Asians work for wages, and this is a little less than 10% Native American. This looks more like 5%. So that's the question. Is the percentage of self-employed the same across these 4 levels of ethnicity? So the null hypothesis is that these 2 variables are completely independent of each other. And that's how we create the expected matrix. So we're going to create the expected matrix by assuming that there's absolutely no connection, that the same percentage of Asians will be self-employed as whites or Native Americans or black. So how do we calculate the expected matrix if we expect complete independence? Well, the first thing we're going to do is we are going to calculate the subtotal for each row, and then we'll take the 565 divided by the total sample size of 5289, and that's how we get 10.7%. So we know that of the population, 10.7% are Asian, and 16.2% are black, and 1.7% are Native American, and 71% were white. Okay, so these are these totals. Then we're also going to do the column totals. So we're going to find this subtotal, take the 553, divide it by the 5289. So we have, like we said before, it looks like about 10.5% of the population represented in this data is self-employed, 10.5%, and therefore 89.5% work for wages. All right. So then how do we come up with this expected matrix? Because this is it. The expected matrix is down here. And that's awful drawing. I'm sorry. So we'll erase that. How do I calculate this value, this 59.1? It's very easy. I take the total number in the population, and we know, so we're trying to calculate the Asian self-employed. So we multiply first by the percent of Asians, and next by the percent of self-employed. So if we get a graphing calculator up here, sorry, maybe we can see the graphing calculator now. So we are going to take 5289, right? I'm sorry, maybe I should move the calculator over here so I can see better, right? We're going to take the 5289 and we're going to multiply by the 0.107, that's 10.7%, and then we're also going to multiply by the 0.105. All right, and we find that there should be 59.4 in this expected cell. So that's what we were trying to calculate. Now there's some rounding error. I didn't use quite as much decimal place accuracy as the program did that calculated these, but you can see that with the graphing calculator how we're doing this. So these are where these values are arising, right? So if I want to calculate the expected cell corresponding to Native American and works for wages, what do? Well, I go down the column to the percentage for that column. I go across the row to the percentage for that row, and then I take the total times 0.017 times 0.895. So I can take 5289 times 0.017 times 0.895, hit enter, and this is 80.4. I'm trying to make sure that I did everything correctly. That's more severe rounding error than I was expecting. But that was getting this value here. So maybe there's a typo. I'll have to double check that. If there is, I'll fix it in the notes. So if you're looking at your notes now and that's different, it's because I double checked it and I made a typo there. All right, so this is how we calculate the expected matrix. What does it mean? Well, this means that if there were the exacts, it's just taking the percentage of self-employed and applying it to all four ethnicities. And then it's taking the works for wages percentage and applying it to all four ethnicities. And same thing looked at another way, right? It's taking and figuring out, well, there's this percentage of Asians, right? So that much percent of the self-employed people, that much percent of the works for wages people. That should be how you should be able to calculate these things. So that the expected matrix is what we would expect to happen, expect the cell counts to be if the variables were completely independent, if the percentages were the same for all four of these ethnicities. Okay, and then how do we calculate the chi-squared statistic? I'm going to show that briefly on the tablet. So let me write the formula down. So the chi-squared formula is going to be a summation of terms. So there's going to be a term corresponding to every cell in the expected matrix, which corresponds to the cells in the observed data matrix. And so we're going to use sort of descriptive variables here. So we're going to have, let me write it this way. We're going to have observed cell minus expected cell quantity squared over expected. We're going to do that for each pair of cells, and then we're going to sum them up. So let's just kind of start this calculation, and we'll see based on the data what that looks like, right? So to do the first cell, we're going to do 49 minus 59.1 quantity squared over the 59.1. 49 49 minus 59.1 quantity squared over expected, 59.1. Plus, and then we do it for every other cell. So the next cell would be 516 minus 505.9 divided by 505.9 squared. And we have 8 terms, eight cells. It's a 4 by 2 matrix. So we're going to have 8 terms in this summation over here. So I'm just going to go dot, dot, dot. But that's how the chi-squared statistic is calculated. But let's think about this term, right? The bigger the chi-squared term is, the less likely the null hypothesis is to be true. Let me see if I can demonstrate that. So when is this term big? This term big is when the data we actually observe, which is 49, is far away from what's expected. Right? So, and it's corrected by the expected, so this isn't quite as big a term as you might think, but still, the further the observed data are away from the expected data, that makes the chi-squared statistic get bigger, and therefore the probability that the null hypothesis is true gets very small. Okay, so the p-value goes down. As the chi-squared variable gets big, the p-value gets small. Okay, so let's take a look at the actual hypothesis test now that we've got all that. So we've got the chi-squared test of independence. Our hypothesis is that employment status is independent of race. And the alternative, if that's not true, then employment status depends on race. Verification, so you can look at the expected matrix, we have it right here, and even though there were some signs of some lower cell counts, none of the expected cell counts actually turned out to be low, so this passes verification, and it's okay to proceed. We had 0% low cell counts, and we were allowed up to 12, so with 8 cells, we could have had 1 out of 8, which would be 12.5% low cell counts, but we couldn't have had 2. If we had 2 low cell counts, that would be 25%, which is more than 20%, and then the data wouldn't be appropriate for chi-squared procedures. So when we run the test, we get a chi-squared statistic of 35.15 and a very small p-value, right? So the p-value, I think that's 7 zeros between the decimal place and the first significant digit. So 1.1 times 10 to the negative 7, no, that's 6. 6 zeros between the decimal place, so 1.1 times 10 to the negative 7. And notice that we are well below alpha, so p is less than alpha. The statistical conclusion is going to be to reject the null. And our real-world conclusion is going to be that we have really strong evidence to suggest that employment status depends upon race. Okay, so the dynamic notes are great to look at. The proportion tests are real easy to run. For example, with the chest cheats, you just type prop.test, and you type in, you tell it the number of successes, the total number of trials, the probability, that's your p sub 0 value, and then you have a place for your alternative hypothesis. And we were using greater. This was the Magnus Carlsen chest cheat example. And when you hit play, it will give you all this information. It'll calculate the chi-squared statistic, the p-value is shown here, gives you the alternative hypothesis that we came up with. So definitely go through there are several really nice examples in the Dynamic RStudio course notes, and you should take a look at them.